Namaste, everybody.
Namaste.
We don't see you, Jacob.
I'll share video in a second.
Okay. Mathematical equations and symbols refer to something existential, something that is inherent in nature, not simply the nature of the physical world with its space, time, energy, and matter, but the nature of possibility. Numbers, symbols, mathematical equations, and expressions are all alluding to these natural dimensional expressions of dimensionality. If those properties of dimensionality are innate to existence, then perhaps we can perceive them directly. Mathematics is traditionally taught in such a way that it almost assumes people cannot see as self-evident through a direct perception of these properties of nature. It almost supposes us because we are taught to go through a sequence of steps to determine answers. If this, then this, altered to this, altered to this, altered to this. And through this chain link process of logical reasoning, we're able to link the initial statement to the final statement and create an equality where we saw no equality at all through our direct experience, but rather deduced an equality from individual steps that they themselves, perhaps we did not see either, but rather may have mechanized and memorized. So if we do mathematics that way, we miss the opportunity to experience the totality, the gestalt of the mathematical concept or truth or elegance, and instead experience a far more superficial quality of mathematics that is basically a collection of rote mechanical techniques that are essentially arithmetic operations and rules. And so we miss the richness of experiencing directly and embodying in our mind our own direct perception of something profoundly elegant, eternally existential, and quantitatively perfect in its precision. Because everything is perfect, or nothing is perfect. But the perfection of mathematics is the fact that it's precisely defined and need not be built by atoms, molecules, and bricks, but rather perceived as a Platonic archetype or potential from which material existence can be reflected. So all of the equations and methods and things in mathematics that we've learned, in the case for those of us who have learned mathematics through the traditional path currently available to humanity, all of those can point to something deeper that we can find and seek. And for those of us who have not learned many of those things, we may begin instead to see things directly through the direct perception and grow our integral core of mathematical comprehension one layer of direct perception at a time until we begin to experience mathematics in its totality directly, not as a sequence of rote, distilled arithmetic processes. So, where do we begin? 3 times 4. What does that even mean, right? These things become so second nature to us that we forget to consciously connect with the reality of what they mean. And unless we meet somebody who's unfamiliar with these topics, it's very difficult to realize that we don't know these things unless we develop a particular kind of skill of learning to apply a kind of intuitive rigor to ourselves and our comprehension, asking no less than a deep, complete comprehension as if we were inventing mathematics ourselves for the first time right now. So 3 times 4. 3 times 4. Does that mean 3 4 times, or 3 times what 4 is, which would be, or that's 3 4 times, or 3 multiplied by 4, which would be 3 4 times? Is it 3 4 times or 3 4 times? In other words, is it 3 4s or is it 4 3s? Is it 3 plus 3 plus 3 plus 3 or 4 plus 4 plus 4 plus 4? So multiplication is one interpretation of it is that it's a repeated addition where the first number and the second number play a role in the quantity of repetitions of that addition. So we start to see things by asking questions like this. Is there some, we could have inferred in basic arithmetic that one way meant the one thing and then another way meant the other thing. So which one comes first? Usually we don't think of that, even if there's some official answer to this, we don't really think of it that way in general. So what is 7 times 3? You just say 21, but you could say, okay, that's 3 7s or 7 3s. Quantity of 7 3s or quantity of 3 7s. Right, so we can begin to look at things more directly like this. And it helps us when we build more complex comprehension. So we can look at very basic things like this, which would be maybe, you could call it the commutative property of multiplication, that multiplication can commute, so to speak, from one side to the other. There are also the distributive property of multiplication, the associative property of multiplication. All of these properties we can see as self-evident, or we can begin to see them as self-evident. Perhaps for the commutative property, one way to see it as self-evident is to recognize that a rectangle of squares that's tall has the same area and number of squares as a rectangle with the same dimensions that's short. So width times height, if we switch the height and the width, we get a wider, shorter rectangle that has the same number of squares. And essentially what we've done is we've either rotated or reflected it about the y equals x line, if you were to think of it that way, about the diagonal line. We've reflected it, or we've either rotated it, both of which produce the final transformation, although the one will have the particular squares in different places compared to the other. But if we're looking at just the quantity of squares, both transformations will produce the same thing. So this may be a way for us to see that multiplication is commutative. So we're looking at basic things, but that may apply to much more advanced concepts in linear algebra, things like that. I'm forgetting the terminology. Perhaps one of you guys know. It's consistent over rotation, but there's another word, not consistent. It's do you know the word, Jacob?
Can can you describe it more? You said consistent.
Yeah, no, that's what it is. Under this transformation, there's no change. And there's a word for that. It's not consistent. It's like it's a common mathematical way to express it. I'm forgetting it right now for some reason.
Basis.
No, it's a word. That's a synonym of consistent. But yeah, in linear algebra. Yeah. So anyway, so there are many topics we can look at this way. So if we're going to teach this, so this class is a mentorship training class meeting, and we want to challenge ourselves to share mathematics in this way. So if you're sharing the Pythagorean theorem, can you see it as self-evident? Now there's a difference between a visual proof
Oh,
and the direct perception.
is the word invariant?
I think that's the word. Yes. Invariant under
It means the
rotation.
same. It means the same thing.
Yeah, I mean it means the same thing, but I wanted to get the official word, not
Right.
the proper description. Yeah, invariant under rotation is kind of a more advanced way of seeing that. So invariant, exactly. Does not vary. It's consistent. Mine's
That
a more positive description.
right. That is a better word because then you get into saying covariant, and then
Covariant. Okay. Yeah. So what I was saying is there's a difference between a visual proof and the direct perception. We seek to see it all in one instantaneous insight of Gestalt perception. It's more challenging. Can you experience that truth as self-evident in your mind with one instantaneous flash of embodiment of that concept, not a sequence of movements in a visual proof, which is closer because each of those visual elements is being experienced rather than some symbol that we perhaps don't know what it refers to, or we're not seeing how it fits together with the rest of the symbols. So visual proof is in the right direction, and I think that's a great thing, but And sometimes it's a challenge to go beyond a visual proof, but the ultimate is the direct instantaneous perception, which I call Gestalt perception of mathematical elegance. The Gestalt perception of mathematical elegance. Can you see it all at once? Y is the derivative of x cubed dx, not dx, of y is ddx of x cubed, the derivative of x cubed. Why is it 3x squared? Do you guys know why? As completely self-evident. No proof, no visual proof, just an understanding of the fact that as the quantity x cubed changes with an infinitesimal change in dx, the infinitesimal change in volume will be 3 times x squared dx times dx. This will be the mathematical koan of the evening. In Zen, I don't know if you guys know what a koan is, but a koan is a Zen question designed to be an impetus for enlightenment and awakening. Usually doesn't have an answer. However, this one has a pretty good answer, although you may say it doesn't have an answer because there's an infinite subjective space with which you can connect with this. Not only are there different ways to see the self-evident nature, perhaps, although I'm thinking of one in particular, but there are various relationships and dimensions of embodiment that one can move into. So in a way, it is a koan because it doesn't have a definitive answer, right? In the sense that all moments are unique and distinct. And once you do it once, it doesn't mean you've done it completely. Every moment you can do it again, anew. So with beginner's mind, which is another element, we can talk about that another day. So we challenge ourselves along the spiritual path of bhakti math, bhakti mathematics, where we do math from the heart. We challenge ourselves to perceive mathematical truth directly, Gestalt perception. So here's this question for you, which is, what is the rate of change in x times x times x? What is the rate of change in that quantity given an infinitesimal change in the value of x? And you can define that rate of change in the quantity x times x times x with the value x and the value of that infinitesimal change, which traditionally we call dx as one unit of abstract structure, is infinitesimally small, which is its own thing. I think of an incremental increase that is infinitely small, and yet substantial. In other words, not zero, it's substantial. It's an infinitesimal increase called dx, which is infinitely small. So how can we perceive this directly? I recommend visualizing a cube whose dimensions are x by x by x, length, width, and height, 3 perpendicular dimensions of length that's filling 3-dimensional space in a cubic structure, and has a volume equal to a quantity equivalent to x times x times x, a quantity of unit cubes, 1 by 1 by 1, filling the space of x by x by x. So just take an example. 3 by 3 by 3 can be seen as 27 unit cubes of 1 by 1 by 1. all but one of them on the surface. Only one in the middle, the rest on the surface. We got 9 on one side, 9 on another side. We got 9 on 6 sides, but then the edges are being shared by those 9, right? In other words, we have 8 corners, 6, one on each, in the middle of each face. And then each edge has 1 as well. And you actually would, if you add them up, you get 8 corners, 1 in the middle, that's 9, 12 edges, that's 21, plus the 6 faces, that's 27, just so happens to be 3 cubed. It's kind of fun. The properties of a cube are 1 volume, 12 faces, or let's say, yeah, 1 volume, 6 faces, 12 edges, and 8 corners. 1 volume, 6 faces, 12 edges, and 8 corners. 1 plus 6 plus 12 plus 8 is 27, which is 3 by 3 by 3. And if you were to say, well, what's 3 to the power of 4, perhaps you would find that the sum of the properties of a tesseract or hypercube would also add to 81. Nice little mental exercise. Okay, the only reason I'm talking about this is so that we can recognize that quantity can be perceived directly in volume, especially if that quantity is a triple product of some kind. Triple product meaning x times x times x, or 3 times 4 times 5. We can perceive that quantity as a volume, as a cube or a rectangular prism. So if we perceive that quantity as a volume, say 3 by 3 by 3, we see it's a volume of 27. If I change that 3 to be a 3 and some infinitesimal increase that is infinitely small and yet substantial, which we can call dx, then we've actually calculated what's known as a derivative, dv dx. But let's really think about this. So dv is, well, okay, so how much did the volume change? If we changed it by dx, the volume changed by nothing, because dx is infinitesimally small, and yet it's substantial. So yet we can come up with some sort of equation that helps us to see how much we actually did indeed change the volume. And we can call that quantity dv, which is an infinitesimal change in the volume. And dv and dx can be related algebraically by some ratio or just some algebraic expression. The ratio of dv to dx, or dx to dv, will, within its, well, it will have a particular value. That's the interesting part. Dx divided by dv, or dv divided by dx. And for those of you who know this will probably be thinking, oh, Adam said dx over dv. I did that on purpose. I'm doing that on purpose just to show you the convention that you usually think through. You need to be able to be fluid like a martial artist that can meet any opponent in any moment, with any situation. They got an injury there, the opponent's this way, they use infinity, the Dharma, to move through that moment, meeting it perfectly, because they are beyond conditioning themselves. In mathematics, we are like martial artists that do this. We are beyond conditioning. We seek to break free of our conditioning, not let it calcify, by flipping things around, dv dx, dx dv. both work. Think about it both ways, right? Maybe even change the letters up at some point. Maybe don't use the division symbol anymore. Maybe explain it to somebody who's learning it for the first time and practice all of that. See, in teaching, we get to learn to see things for the first time and prevent the calcification of conditioning so that we can meet each moment anew in freedom in a way that is able to answer novel questions and in a way that keeps us experiencing the mathematics more deeply, which is essential to developing the lucidity that we're using to become conscious and awakened. Ultimately, enter into nirvana and samadhi and achieve moksha and all those things that we hope to do in this lifetime. Perhaps we hope to. Any degree of increased consciousness, any deconsciousness is positive, is good. Deconsciousness, de-time, the ratio of changing consciousness infinitesimally to the ratio of the change in time. As long as that's positive, I think we're on the spiritual path. And mathematics, of course, helps give us metaphor through which we can understand everything in life. Or let's not say everything, but we can certainly apply the metaphor where we choose as much as we can. Many things. So, okay, so if we're looking at this cube, the cube has, we actually can be a specific cube. So 3 by 3 by 3, it's got a volume of 27. I increase the 3 by a factor, not a factor, but by an additive incremental increase of dx, which denotes an infinitesimal, substantial, non-zero, infinitesimally small quantity. What's my new volume? Would not my volume be 27 plus dx times something? Imagine that dx is actually not too close to zero. Just make it very thin. Just to help your mind visualize this and apprehend it. Oh yeah, Jacob, we're not drawing your diagram this time.
That's fine. That's fine. That's fine this time.
So yeah, but I think it's a nice mental exercise for anyone listening to visualize this. So we have a cube, 3 by 3 by 3. It's got 27 1 by 1 by 1 cubes in it. And we're increasing almost like a paint thin layer on one side. Well, not on one side. Well, we're increasing the x in one direction. That's what I mean, right? So we don't increase the x in both directions. We just make it longer from 0 longer, right? So it's 3 and now it's 3 plus dx, not dx on both sides, right? It's just one side. So if we did that, we're basically doing one side, one side, and one side. And so we've actually only changed, we've only added, we've kind of added 3 layers. Right? Because each of those creates more volume on one of the sides of the cube. So since we've added in 3 places, we're actually adding more volume to 3 sides of the cube. And the volume we add will be a very flat rectangle with dimensions x by x by a very small height. So it's going to be a square. Well, it's not a rectangle, actually. It's a rectangular prism that is square rectangular prism. It's like basically a very flat square piece of paper. What's the height of that square piece of paper? Dx. And the dimensions are x and x. So x times dx. Length times width times height or depth. And that's a volume. But that volume, because dx is infinitesimally small, that volume itself is infinitesimally small. But the change in volume then, if we were to calculate it based on this elusive dx value, would be, Jacob?
So we're calculating the new volume.
Yeah, well, not the new volume, the added volume.
So we had our x cubed for an x length of three units. So that'll be a volume of 27, and then adding our uh, our derivative volume.
No, we just want the change in volume, so you don't need the 27. But I wanted to see if you had already got it. So think in your head. So we have a cube that has an increased volume on 3 of its faces.
Mm,
The volume that's increased is equal to x times dx on each of those. So that's 3 times x times dx. That's the increase in volume.
right.
So 3 times x dx equals dv.
Yeah. Yeah.
Now, the question you might ask is like, well, what about those little edges, right? Because if you increase the square, if you add something on 3 sides and it's relatively thick, you're going to have a little groove on the top. Well, there's going to be 3 grooves where we would have to fill in, and then the corner itself is going to be missing because we've extruded the faces out, but we haven't moved upward. We haven't filled in the space between those extrusions. We've extruded them, extrusions. We've extruded them, but because we've extruded them infinitesimally small amount, those things don't actually come into existence anyway. So you could perhaps say it's 3 times x times dx, and then those extrusions have those grooves. There's one long one, which would be a dx times x. And there's 3 of those. So we can say plus 3 x times dx in each of those. And then the corner would be just dx times dx 3 times.
Mm,
Right? But the dx of a dx we're seeing here is infinitesimally small, and therefore it has no relative size compared to what we are doing, because what we're doing in the very initial moments before we even create that groove. It's what happens in that instantaneous beginning of extending the x's by dx. That's what dx is by definition, because it's a limit.
right. Yeah.
So dv equals 3x times dx.
Yeah.
3x squared dx. And if you want to know what's the ratio of dv to dx, it is 3x times x, 3x squared, 3
Yeah.
faces. And in the case of the 27, it would be 3 3x3s, which is
Right.
also 27 in this case, but that's a coincidence.
Yeah. Total is 54,
What was that?
and then the total will be 54 added to that original volume.
Nope. 54. Oh, no. 27 is, we should use a different example because it's going to be confusing. Let's do a 4 by 4 by 4. So 4 times 4
Right.
times 4 is 64.
64. Yeah.
And each of the sides is 16.
Yeah. And
3
then that derivative is 3 times 4 times 4. That's 48.
48. See, now it's a different value. Okay, so
Mm.
we'll say the ratio of
Oh, okay.
dv to dx is 48. It's a
Okay.
ratio. The ratio of the change in volume to the change in the side is equal to the three faces themselves.
Hmm. Oh. Uh-huh.
There you go.
Yeah.
Good.
Yeah. 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 I see. I see. Okay.
So y is so derivative, the word derivative means the rate of change in a mathematical expression divided by the rate of change in its independent variable.
Right. Yeah.
Well, what is the rate of change in the mathematical expression, which is equal to the volume of a cube divided by the rate of change in its independent variable, which is the side length of the cube? The answer is 3 faces, all of x by x, which is the area of a face of that cube.
Yeah.
That's the ratio. Of course, you can also think of it in terms of dx dv, which would be 1 over 3 times x, or 1/3 x to the power of -2, which is obviously not as natural to say, but but you could look at it that way if you wanted to challenge yourself. The rate of change in the independent variable as the value of this expression changes infinitesimally. This is what I would call the direct perception of the power rule. If you could imagine a square, it would do the same thing. An x by x square, that's 4 by 4, will change by 2 lines on the top and the side, let's say, or bottom and the other side, or bottom on the same side. There's a few ways you can do it. So it'll change by those 2 little, very slither thin rectangles that are dx by x. So we'll have a change in area, a dA equal to x dx plus x dx, or 2x dx, or 2 edges. 2-dimensional
Yeah.
shape, 2 edges. Good. 3-dimensional shape, 3 faces. 4-dimensional shape, 4 volumes. Right? And
Yeah.
a volume is a 3 cubed. So what's the derivative of x to the power of 4, which would be, you can imagine a tesseract. So I mean, this is a much bigger challenge than just having somebody memorize, bring down the n, and then say n-1 in the exponent, right?
Yeah.
It's a bigger challenge, but in a way, it's also much more efficient, because what
Right.
you're doing is you're actually developing your mind, which is the whole point here. And when you develop your mind, then you can think about things better. That's the whole point. You don't want to just become a proficient robot at taking instructions from somebody, and you want to work at a company and just take instructions. That's not even as much of a job anymore. With AI, you'll be very obsolete doing something that superficial, right? So you need to have deep problem solving abilities, and ability to apprehend abstract truth through Gestalt perception, right? Then you have a valuable contribution when you arrive at Tesla and tell them that they can increase their acceleration by 0.03 if they do this because you thought of it differently, right?
You're spanning your basis of your mind.
Oh, nice metaphor. I don't understand why you said the metaphor, but spanning the basis of your mind.
So that
Oh,
you said that we were opening our mind and not kind of thinking it mechanically one way.
are you adding another dimension to the basis? Is that what you mean?
Yeah. Yeah. So
Oh, okay.
we're
Because if the basis is if you just alter the basis and it still spans the same space, that doesn't, yeah, okay,
yes.
that's what you mean by expanding. Nice.
Yeah. Yeah.
Yeah, so how can we see a tesseract? Well, you could try to visualize one, but you can also think of it. Okay, so let me there when we look at parts of it. So a tesseract, a cube, is in 3 dimensions. Therefore, it has three orthogonal axes that run along its edges. And because of that, it has three faces that grow. And so the dimensionality of the object that's filling that dimensional space it's embedded in that. If an object embedded in n-dimensional space, so a cube, which is a three-dimensional object embedded in three-dimensional space, that is created by those orthogonal axes, right? By definition, a dimension is made by a number of orthogonal axes, which you may consider the basis, right? So a tesseract is in fourth dimensions with four orthogonal axes. And when the length of each of those axes grow, it increases on one of those. Each of them contributes to increasing face, but it's a voluminous face in this case. The tesseract is enclosed by a voluminous face on either side of each of those dimensions. Just like a cube, the reason a cube has 6 faces is because it's 3 dimensions times 2. It takes 1 on each side to enclose that volume. A square has, think about this. How long ago did you learn about a square? And now look at how we're talking about this. A square has 4 sides because 2 dimensions require 2 sides to enclose an area. And a hypersphere or a tesseract has 4 dimensions and 8 voluminous sides, enclosing a hypervoluminous space, 4th dimensional space. But we extrude it only in 3 directions with the cube because we don't go both ways. So we, in this case, extrude only in 4 dimensions, and each of those dimensions is extruding by a cube times dx. So x cubed dx, 4 of them, 4x cubed dx equals d8 dh hypervolume or dvh. Now, if you were to have an n-dimensional space, 17 dimensions, the 17-dimensional cube is comprised of six 34 16-dimensional hypercubes as their faces. I believe I'm correct about that. How am I seeing this? I'm not totally visualizing a 17th dimensional cube. That would be extraordinarily arduous. Just stick to the 4. I don't even think it's possible to do that. 4-dimension is a great thing to try to peer into and dip your finger in if you can try to turn it outside of 3-dimensional space. 5th dimension would be an extra reach again, but you start to see the general structures of these things. Dimensionality is orthogonal. That orthogonality requires something on each side to enclose the space within that linear dimension. This is the power rule. We're telling the rate of change as a ratio of the change in volume to the change in the independent variable, the side, or x. dv ds, dv dx, however you want to say it. So we now are perceiving the power rule directly. You can expand upon this. You can start to say, well, what about the product rule? What if I have an x and a y? And I change them both, and we get a dy and a dx. Or an x, a y, and a z, and I get a dy, a dx, and a dz. See, I haven't even thought about this, that I could tell you just by looking at it. I'm reading the fabric of the universe, man. Open your mind. Sit back, look at the stars, and read the fabric of the universe, the galactic encyclopedia within your mind. Commune with Pythagoras and Euclid and mathematicians of times past, times in the future.
Ramanujan.
And Ramanujan, yeah. The whole point is you're communing with all sentient beings. We're able to peer into abstract perfection when you read that. So let's see if I can get this right. The triple product rule. I mean, maybe you guys want to try it. I don't know if you can see it. The triple product rule would be to see what we did with the cube with a rectangular prism. It's pretty cool. It's really cool that you can just look and read this. It's really cool. Oh, it's so cool. So in a moment, I will say it. Perhaps you want to write it down if you see it. The funny thing is, I'm just going to read it. So I haven't stored it in my brain. I'm going to read it as I say it. I know I can read it as I look at it. So the answer is dv equals xy dz, xz dx, yz dx. Wait, let me say it again. dv equals xy dz, xz dy, zy dx, all added together. I mean, it's interesting because I'm calling it the product rule, and perhaps it's not triple product rule, but I'm doing it. I'm asking what dv is, right? Now you could say,
Adam, does not the change in volume depend upon from which side we are seeing it?
no, the volume is growing based on a dv. I mean, the change in volume is dependent on the change in x, change in y, and change in z, invariant under rotation, an intrinsic property to the object, right? Doesn't matter if the object's flipping through the air. If we're growing those sides in that way, we're growing the volume in that way. Usually the product rule is talked about as an equation of derivatives. And those derivatives are like, I mean, you could try to look at it as derivatives like dv dx. Okay, so if I had something like I just think of the basic equation. What's the derivative of f of t times g of t? And you'd say it's f prime of t times g plus g prime of t times f of t, right? So we're relating, in that case, f prime of t would be df dt, right? So really we're kind of, if you were to look at it in that context, and the way I was looking at it was very, very simple and direct. But if you look at it in that context, you say x is a function. They're like, maybe they're all growing different speeds. So x is a function of t. We kind of need a fifth variable here, a dt. We've got dv, we've got dx, dy, dz, and then dt. So if you say x is a function of t, so x is changing relative to an incremental change in time, then dx dt will have its own value, right? And so in a way we can just divide everything by dt. That's my point. Everything. So I think yeah.
And I was
Yeah.
thinking about this. Okay, you complete Adam. I don't want to speak.
Okay. Um, well, we're finished on time. So Karan, you want to say really quickly what you're gonna say?
When we think about the higher dimensions, for example, fourth dimension, taking the derivative of x powered 4, we can think in terms of x squared times x squared, the square of x squared times x squared,
Mhm.
and do the derivative on it and get the result. That is it the way that we comprehend for the higher dimensions to
No,
reduce the
no,
dimensionality? And
I wasn't thinking of them as pairing them, because then you think of the fifth dimension as x squared times x cubed. Why? I think of it as 5 orthogonal dimensions. And the goal is to play with it. Let me know what you think. I mean, it's interesting to say that x squared, two squares that are completely orthogonal to each other, which you can't do in three-dimensional space, right? In three-dimensional space, you have a square and a square. There's parallel going, like it's here, they're parallel there, they're parallel there, they're parallel there, right? If you make them completely not parallel in any direction, two squares that are not parallel will actually require you to get into the fourth dimensional space, right? So I guess it does move you in that direction. So, all right, let's do our meditation. This was a really fun talk. Thank you guys for following along and listening. I wish I could talk to people more. Fran, thank you. About these concepts. I love it. All right, let's listen to some M83, one of my favorite songs. Namaste, everybody. Thank you so much. Good job today.
Thank you.